Okay, good afternoon. For those of you that weren't here for the first session, my name's Duncan Baker-Brown from the University of Brighton and BBM Sustainable Design. I'm an architect and academic, and I've focused on closed-loop systems and sustainability for over 25 years. I'm curating this event, and I've known Harry, our guest keynote speaker, for about 10 years, and he's focused on genuinely deep retrofit projects that generally respond to the climate emergency. So that's why he's speaking today, because that's our biggest challenge. The construction industry basically consumes 50% of all natural resources mined and harvested every year. And we're pretty much responsible for 45% of all emissions. Of all the cities around the world declaring a climate and ecological emergency, they then say they want to be net carbon zero. They then say, quite often, that they're going to retrofit their existing places. How they're going to do that is anybody's business. I don't know. But Harry's got a lot of the answers. So he's set up an organization called RAFT, which is Retrofit Action for Tomorrow. He's going to talk about that. His practice is called arboreal architecture, and he's our keynote. Over to Harry.
Duncan, thank you very much. Can you at the back put your hand up if you can hear me just fine? That's great. Okay, can I just encourage any of you just to be brave and come to the front? There's 4 seats here that are completely free. So, if you come a bit nearer, I feel a bit more connected to you. So go on, be brave. No? Nobody's being brave. Okay. All right, so thank you very much for the introduction, Duncan. I've got a fairly intense presentation to give you. Before I start, I'd just like to, would you mind putting up your hands if you were at my presentation for the ASBP on Thursday last week? The Association for Sustainable Building Products. Okay, none of you have put your hands up, which is excellent, because there's a little bit of duplication of what I presented there, although there's a lot of new material as well. So that's great. So I can now tell you everything and not feel I'm repeating myself. So yeah, my practice is arboreal architecture, and for the last 10 years, I've been practicing deep retrofit, which is really a mission to upgrade the thermal performance and operational energy of existing buildings. And in a way, today I'm going to take you on a bit of a journey of my own self-discovery through trying to reach low-carbon solutions for the built environment. So I'm a co-director of arboreal architecture. I'm also a co-director of an organization called 1540. We're a collaborative of architects working on larger projects. I'm also the co-chair of a technical working group for the UK Centre for Moisture in Buildings, and that's on the Retrofit group. I'm a technical expert at the Sustainable Traditional Buildings Association, and I do recommend you look up their website and all the resources there, which are very useful. I'm a REBA architecture ambassador, and I've been working with schools and teaching children and engaging with schools. And that led to me founding RAFT, which stands for Retrofit Action for Tomorrow, which is a not-for-profit organisation. And I've just started working with the first school in Lewisham, and we are working to make the school zero carbon. It's a very, very exciting project. If anybody's connected to schools, please come and talk to me afterwards. So the other thing is that I'm a DIY retrofitting architect, which means I practice what I preach. And I've spent pretty much every Sunday for the last 3 years retrofitting my own house. So my house is one of the case studies. So this shows a timeline of the of various projects that we've worked on. So this is a chronological in terms of the types of buildings we've worked on. And really this slide is there to say that, well, a lot of buildings need retrofitting, a lot of different typologies of existing houses, ranging from solid wall listed Georgian houses to cavity wall 1920s semi-detached houses. You'll see the one that says 1988 is a timber frame self-built house. That's one of the Walter Siegel houses on Walter's Way. And we're about to start on site a retrofit of that house. And you won't believe it, or probably most of you will believe it, given the performance gap of most modern construction. But we're also working on a retrofit of a 2012 house, which is the one on the right. So just very briefly, I'm going to introduce 4 projects. It's just 2 slides per project. And it's just to give you an overview of stuff that's actually been achieved in the past. So this is a grade 2 listed semi-detached house. And we achieved the AECB silver standard, which is 40 kilowatt hours per meter squared for space heat demand, and achieved an air tightness of 2.1 air changes per hour at 50 pascals. So that's pretty good air tightness. It's had a listed interior. We worked with Conservation Officer in Historic England to achieve that. This is my mum's house. So again, we achieved the silver standard for this project. And we slightly reduced the level of air tightness, so we didn't tape all joist ends with air tightness tape to reduce leakage at joist ends. And we lost about 1 air change per hour for that. So we sort of started to build up over time a kind of a feel for how deep do we need to go, how invasive do we need to be to achieve what result. This is a passive house, a certified passive house retrofit, Enofit, mid-terraced house in West London. And we only just scraped the target value of 1 air change per hour. It's quite challenging when you get down to the lower levels of air tightness on existing buildings. And yeah, that was quite a journey. We've also worked on this rather wonderful building in the City of London, where we've achieved a pretty similar standard, the AECB silver standard, and just below 3 air changes per hour. That has MVHR. It's actually a 7-story building just next to St. Paul's Cathedral. Very jealous of that project. So on to 2 case studies. The first case study is the UK's first step-by-step passive house retrofit, which is of my own house, and we're on step 3 of 5. It's a mid-terrace, 1978 cavity wall building, mostly solid wall at the front and cavity wall at the back. It's actually on the lee side of a hill, so it's got quite low wind exposure. It's quite interesting to really try and understand the topography and geography of where your building's sited and how that affects how much heat losses you might get through ventilation, for example, because we really don't get as much wind as they do on top of the hill. And it's also got very good exposure to useful solar gains, so that's the low winter sun heating through that large window you can see at the front. So, as I said, mid-terrace, it's got a TFA. TFA stands for treated floor area. It's the passive house standard for measuring the area of a building. We're going to be adding a studio, so the garage will be converted. It's 3 stories. When we moved in, it was very poor decorative state. It's got a little odd jig in plan where the buildings are sort of set back, so there's a little bit of exposure of party wall at the back. You can see where it steps back at the front, so therefore the back corner is exposed. And at the time, 1978, the only requirement for insulation was about 100 mil of fiberglass in the loft. And in a bit, I'll show you a slide of that. So yeah, really no insulation in the house. And I really want to emphasize to anybody embarking on a retrofit project that retrofit ready works is incredibly important. A lot of people say, Reno, I want to do the right thing and I want to retrofit my house and I want to put some insulation in, and that's the first thing they're thinking about. And I always say, well, the first thing you want to think about is getting your house maintained well, do all the repairs that are needed, make sure the walls are dry before you start doing any works to it. So most of the layers of the house were stripped out before we moved in, so we did all the really nasty, dusty stuff before we moved in. This is the Enofit verification. Quite complicated to do a step-by-step retrofit using the passive house methodology, but very rewarding and very thorough. So this shows the 5 steps. We're on about halfway through step 3. So what this needed was a very careful management of the building, the different steps we're going to take, the order we're going to take them, the relationships between putting insulation in and windows or ventilation and maintaining good ventilation whilst those works are taking place. So it needed quite a lot of thinking to get this right. And the really great news is that as of today, we're actually performing better than designed in terms of actually measured energy. So it's very encouraging that PHPP, the Passive House Planning Package, which is a set of Excel spreadsheets, is actually very good at predicting space heat demand in existing buildings. So this is a little slide that just shows all the things we've done with the building. And you'll see we've had lots of people round. So it's been a project that I've shared very widely, wanting to help people understand what retrofit's all about. And that sharing has involved getting people from bays, the government department bays round, to getting some local school children round. So it's been very open. And I may open it this summer for International Passive House Open Days if anybody was interested in visiting. And don't expect a grand design, it's just a simple retrofit, but there's lots to see. So there's the floor plans. The orange was steps 1 to 3 and the blue was after, so we're doing it incrementally over time. And then there's a section that shows the orange, which we've done already, and the blue, which is on its way. So this scheduler in the Enefit Retrofit Plan set of documents that are needed is actually an incredibly helpful document, and I think all architects should really be thinking like this. We've all been exposed to this type of thinking in our architecture education, but it's very rare that you'll actually see architects looking at the age and the service life of all the elements in the building. So this exercise actually really helps you to understand all the different layers of building and when might you want to put solar PV on, for example, and how does that relate to the existing roof coverings, and might you want to try and coordinate those two. So it's about thinking deeply about the layers of building fabric. So we've installed MVHR, mechanical ventilation with heat recovery. I won't explain how it works. I assume, actually put your hands up if you do understand MVHR, or don't. If you don't, you're welcome to come talk to me afterwards if you want to understand it. So I drilled all the holes in the house myself. I installed the whole system, including hanging the box on the wall. And I got a little bit of help from this guy, who's been pretty instrumental in the project. He was talking to his mum in the garage there, but these are some of the pipes that circulate the air in the house. And the MVHR is a box that's in his bedroom, and he's actually got really engaged with it, and it's really fun to take out the filters and look how black they are and think about how much dust we're reducing and PM 2.5s are reducing in our house. And when people come to visit, they all love this cupboard and they love looking at the filters and taking them out. And it's interesting how important ventilation is to people. Despite the fact that probably most of you live in houses with too high relative humidity and nasty trickle vents that may or may not be blocked. So my son produced this lovely poster. His MVHR layout was probably better than anything I could do. And you'll see on the top left, he's showing the fresh air coming into his bedroom, dropping in from the ceiling, and the bottom right is his mum showing the air being extracted through the kitchen, and that has a fleece filter on it to stop any grease getting into the system. So that's before and after. That's what we're stopping coming into our house. And last summer, during the heat wave, we got these lovely triple glazed inward opening windows that can be opened massively with a flying mullion, and so we get really fantastic nighttime cooling, which is great. But we've been using this air visual carbon dioxide and PM 2.5 air quality monitor. This is us taking it on the school run to look at the profile. But we've also been monitoring indoor air quality. And that enormous yellow spike there is when we had the windows open for nighttime cooling. So we had the windows open a lot, and our air quality went down, and that's pretty dramatic, isn't it, to see such a big decrease. Having said that, 30 is still not a terribly high number. It's not dangerous, but it's still worse. That's what the insulation looked like when we opened up the ceilings. That's basically a non-airtight top floor ceiling with holes in it, let's say the electrics for the lighting in the bathroom, and that's just humid air tracking through, being drawn out by wind blowing over the top of the house, pulling warm, moist air, condensing on cold insulation and growing mold. So pretty nasty stuff. So that's what it looked like with the insulation taken out. And we then put in air tightness boards, total vapor block with taped edges and taped to the walls. So a lot more help from my son, as you can see. So we put 300 mil of insulation in the loft, and this is the store floor system, which is very good. I installed it myself. So most of the windows in our neighbours' houses are single glazed, so they suffer massively, all of them, from condensation in the winter and terrible overheating in the summer. We had that, which is really horrendous, all these tiny little fake mullions, really nasty, and all the seals had gone, very, very poor. We've now installed lovely triple glazing, and they are, it's really, really nice to go from a really crap window to a really, really good window. It feels great. So we've installed cork insulation. Cork has one of the lowest impacts, carbon impacts of any insulation material. Cellulose is lower. But in terms of sequestration, it's not as good as wood fibre, but it's the lowest impact in terms of getting the material to site. We've installed it as a finish, so we've had a bit of fun with it. So we've done some careful details to manage the moisture profile of the wall. But I very carefully laid this out, and I really wish more of this was done. Valuing material, looking after it carefully, not just diving in and starting to cut and making mistakes, but just really valuing all of it. I laid it out, on the driveway before I installed it. I saved all of the offcuts of the insulation, and I insulated a whole nother wall with them. So we did a series of watercolors. This is basically me on a kind of Tuesday or Wednesday night preparing for the Sunday's DIY. So I would work out the detail, and then I would be ready on Sunday to execute the detail. So we overheat in the summer. The whole house as a whole, modeled in PHPP, Passive House Planning Package, doesn't overheat, but the front rooms do overheat. So I wanted to solve this for this summer. I've installed sensors throughout the house, and I've got the whole profile of temperature from last summer, and we're going to better compare it to this summer with solar shading. Now, I looked at a range of possibilities for solar shading, including electric blinds. A lot of them are actually UPVC. They need electrics, needs extra scaffolding, they need servicing. What a palaver, External shading needs innovation, and I've come up with a super low-tech solution, which are basically sails. So I'm going to go sailing when it gets very hot. So I've been working with a company called Timber Intent, and we've designed these external fixed shades. They've got really, really beautiful detailing. I was told this is one of the best sail makers in the country that made this. So it's stainless steel fixings. So we've got eyes. So I managed to fix all this by hanging out the window in a harness, and no scaffold, super cheap, about £1,500, about £500 per blind. And basically, when it gets super hot, I'm going to rig these blinds, and they might be up for a couple of weeks, and then when it cools down again, I'll take them down again. So it's a different way of engaging with the building. It's more engaged. I open the windows, up go the sails. Be interested to see what the neighbours think. You'll see that there's a scallop at the bottom of the window, so that's to see out. When it's sunny, actually a lot of light comes through these, so actually the ambient light inside is quite nice, and it's a little bit reminiscent of Sir John Soane's museum with all his yellow glass. So that's what they look like from the outside, and obviously I'm looking forward to see how effective they are. I'm pretty sure they're going to be very, very effective. They're also within the plane of the facade, so just in case anybody's wondering about planning permission, they're within the plane of the facade. And I'll take them down if anybody complains. So this main window is a bit more challenging because I can't reach. So the reason why those blinds work is that I've got inward opening windows, and I can access it and hang it very easily from the inside. Whereas this sliding door, there's a corner that's a bit more tricky to get to, that top right-hand corner of the door. Before I installed the door, I did actually install some lugs at high levels. So there are 2 metal connectors that were installed, and I didn't know what I was going to design, but I just put them in, and thank God I did, because now I've got something to connect this blind to. So we'll have something like that. And then, of course, I need to reach that corner, and again, I've turned to boat technology. So I've got a boat hook and a mooring hook, so I can just hook that corner on and then hook that corner off. So I made a pole, and I can easily access that corner. So there's a number of sensors in the house. I use the OmniSense HydroTrack system, so they're wireless sensors. I've got some in the first listed building I showed you earlier on. I've got 22 sensors in that building, and they were installed in 2013, and they're still beaming back data and still going fine and giving us all the moisture profiles. So I wanted to do the same for my house, both for the interstitial profiles of the walls, but also for temperature. So I've installed it in the loft. I've installed one in my neighbour's loft, got them in different front rooms. So we're kind of able to then produce data that kind of verifies some of the thinking that we've been having. So that's one of the sensors. They're screwed into a block of wood, which is a block of wood from the house, so I get the actual moisture content of the timber. That's what an 8-year-old's face looks like when you drill a big hole in the wall. So that's drilled in the wall so that I can put a sensor in so I can see what's happening behind the cork. So that cork went back in. And then this is a profile showing when it was the mortar was put in. We had very high humidity on the left, and then you can see it gradually drying out, and then it gets a little bit wetter during the winter, and then it dries out again in the summer. So when we bought the house, one of the conditions of sale was that the tree stump, which you can see on the right-hand side, there was a tree there, a giant Leylandii tree. One of the conditions of sale was that was cut down. We cut it down, but I didn't want to lose that material, so we had it slabbed with a mobile chainsaw, and that's what that blue pile is at the back. So that's about 1 meter cubed worth of Leylandii timber, which was air-dried for nearly 3 years, and then this is us taking it down about 2 or 3 months ago. So you can see it's stickered, beautifully air-dried timber, and it's actually rather lovely. So we took it to a local joinery in Forest Hill, just around the corner. We very carefully set out what we wanted to cut. Sawdust went to a local stables. It then turned up back at the house. I wanted to keep every single offcut, so I wanted all of the material. So you'll see all those sticks on the left-hand side. I'm finding uses for all of those. And then in terms of materiality, I think when you work more closely with materials, in particular wood, you can start to feel it and look at it, and we decided that we were going to keep this very, very rough texture of the mobile sawmill cutting through. This is chainsaw, and so we've kept that on the top surface, and we'll be adzing in between where the planks for a deck. So we're going to make a deck, and we're going to support it on some screws. So my son holding a screw, big screw. We're drilling holes into the ground. So I just couldn't bear to put concrete in the ground. It's just no way I was going to do that. And we wanted something that would be reasonably long-lasting and very simple to install. So, even an 8-year-old can do this. So we're going to have a lovely deck at the back in the back garden. When it stops raining, I'll put those screws in and construct the deck. So just a very last story about the project. We really didn't want to lose any material from site, and so this is a leftover spiral metal duct that was used for the MVHR, and I free-cycled it, and then I don't think that worked, and then I freegled it, and then somebody turned up. Somebody said, "Yeah, I'd love it," and I was great. So she came round, she was delighted with it, and she put it in her car, and just before she drove off, I said, "Oh, by the way, what are you going to do with it?" And she said, "It's for my new kitchen." I said, "Oh, really? All right, great. Where's your new kitchen?" Uganda. So 6,500 miles away. So she was, for £15, she was getting that into a container, and it was going to be delivered to her house in Uganda. And she is building a house in Uganda from FreeCycle and Freegle from London. It's pretty incredible. Right, second case study. So for a long time, I've been very focused on energy, using passive house methodology and doing deep retrofit. The last few years, I've started to ask the question about what is the embodied energy of the retrofit project. How much carbon are we burping when we create our projects? So this is a case study for a couple in Bourneville, just south of Birmingham. There's the site in red. So it's actually right on the edge of the Bourneville Conservation Area. They're opposite it, so the houses on the bottom right are in that area, the houses on the left are not. So it's a 1901 house. In the background you can see the Cadbury factory. There's the front facade. It's got some really lovely brickwork and mouldings around the windows. And the back has actually got a really lovely warm red texture. And in years gone by, I would have said, right, Victorian house, okay, internal wall insulation at the front and external wall insulation at the back, which is fairly standard practice on a lot of projects. And quite often it's relevant. But in this case, we really felt that the red brick was adding a lot of character and quality to the rear building scape. And also feel that sometimes external wall insulation can kind of ruin that appearance. There's a number of issues around junctions and party walls and things like that, and there are also points of potential risk of ingress of rainwater. So I sort of, on this project, we said, look, let's not do that. Let's do internal wall insulation. In terms of internal qualities, we've got some rather lovely quarry tiles in the hallway, some lovely mouldings. But a lot of the rest of the house has been stripped out already or has had different layers added. So in terms of the scope of what we were looking in terms of how we're measuring the carbon, we didn't look at the whole garden. We looked at the house plus a little bit of the garden. So that's the red boundary. There's a plan of the house. It's fairly standard. It's got a rear extension, a rear addition, which is a kitchen, and then it's got a little extra add-on that has been added possibly in the 1980s. So there's our client at the allotment, and our client doing a bit of DIY. These are some materials that they've already either found or recycled or sourced from local free cycle. On the left are some pallets that they've turned into some potting shelves in their greenhouse. On the right are a series of pieces of timber that they've reclaimed locally. Here on the left you've got the laminate flooring that they pulled up and they didn't put it into the skip. They carefully stacked it, put it in the loft, waited patiently until somebody claimed it on, I think, eBay. They even sold that. So there's the floor afterwards. And this is a carbon profile of our client. They're already significantly lower. This is household. So they're already significantly lower in terms of their carbon profile of the typical household. How are we doing for time? What's the time now? I don't have a time here. Perfect. So this project was rather ambitious. It's got a fairly small budget and a very big ambition. So we've got the client at the top there, George and Sarah, and we introduced some project partners for this project. So we've got Jane Anderson from Construction LCA. She's doing a PhD on carbon life cycle analysis in boundary projects, boundaries in pushing the boundaries, I think. So this was a deep retrofit, and so she's working as a partner with us on this project. We also had Etude. They collaborated with us in terms of the WUFI high growth thermal analysis of the proposed insulation on the solid brick walls. And we also collaborated with one of our connections at UCL, somebody who's doing a master's thesis on the project. Not only that, but we also were testing a BSEN and some of the STBA pre-retrofit condition surveys. And we also carried out our own internal thermal performance assessment. So again, before starting projects, we want to fully understand the house. So we want to look at everything that's going on there. The blue are comments about moisture. Most houses have some moisture issues somewhere in them. So we want to be very clear about what the existing conditions are before we actually go in and do work. This shows the proposed retrofit strategy. So we're looking for thermal continuity. We're looking for air tightness. And you'll see here a hint of the little extension that we've created at the back, which is on the left-hand side of the image. And then we model our buildings using Design PH, which is a piece of software produced by the Passive House Institute, which plugs into SketchUp. You might all be familiar with SketchUp, 3D modeling software. So we model geometry in SketchUp, and then we run this software, and we can look at the thermal performance of the house. So this is the existing space heat demand, around 300 kilowatt hours per meter squared per year. And then the proposed, we then model the building again, and this is around 82. So in terms of the existing and proposed energy required for heating, space heat demand, we're looking at about a 72% reduction. So we're looking at about 80 kilowatt hours per meter squared per year, which is actually double the AECB silver standard, and it's significantly above Passive House. Passive House Enefit is 20 or 25 kilowatt hours per meter squared, and Passive House is 15. So we're significantly above those levels. But this project wasn't about pushing on energy and insulation. It was about a holistic view in terms of thermal performance, historic character, and carbon. So we're trying to balance those three and being much more conscious about a holistic view. So we developed and I'm not expecting you to read this, there's a couple of details, I'll see you go like that. So we developed a kind of tool, quite dry, but actually very useful, which is a schedule of project decision making. So what we did is, wherever we felt there was a thermal, carbon, or historic fabric moment, as in, what do we do with that? We thought, well, let's carry out a rigorous assessment of each measure. So this was about carrying out a historic assessment of that measure. Then we did a carbon assessment of the measure, and then we did a thermal assessment of the measure. And then we tried to find balances. And there's been a number of moments where we've perhaps pushed the energy a bit harder, and our client, he works in energy, and she works is a senior conservator at Historic England. So she's on the kind of historic building fabric side, and we had some moments where there was a kind of dynamic push and pull between, how are these competing drives working against each other. And we worked out that after the retrofit, the beautiful quarry tiled floor, so after insulating the house, the quarry tile floor is going to add about 20 to 25% of the heat loss of the house. Because of course we've insulated the whole house, so suddenly that uninsulated part of the house is actually, really, really losing a lot of heat. And nevertheless, that we're not taking it all up and throwing down insulation. We're going to leave it as it is, and they're accepting a cooler space. We're going to monitor it in terms of moisture, and in a way, the client was very clear about this. They wanted it to be an example of a bit of a compromise that needs to be made in existing buildings, and be representative of the kinds of decisions that, let's say, all of you, when you decide that retrofitting your house is very aspirational and is the right thing to do, then there'll be those moments. And so we're just trying to explore that. So on the left, you'll see that there's a series of actions considered, and then we always said, well, what's the least we can do? Yeah, so we're not maxing out extension and making the biggest kitchen, dining, living space ever. We're actually trying to do the littlest, smallest, understated intervention we can do on every decision. Yeah, so it's a different mindset. It's not like my great big beautiful architectural dream extension that's I'm going to try and get into the magazines. It's about how can we minimize carbon? How can we produce a space that's still lovely for our client, delivers what they need to unlock the spatial issues that they're experiencing in the house, but that doesn't blow the budget in terms of an enormous carbon burp. So this is a little process diagram of all the things we've done. So we've added insulation, we've added mechanical extract ventilation. We've got new high-performance triple glazed windows, replacing the existing windows. But we've been really careful about recycling the glass, actually reusing the glass. So we produced a schedule of all the glass in the building, and we're actually using it in the extension. So there's a whole series of elements are being reclaimed. And then we're building the extension from locally sourced timber. Big story about foundations, which I'll come to in a bit. We're recycling the window frames. We found a local UPVC recycling center. We're going to be cutting the frames out, and then we're going to be using the glass in the extension. We're reusing bricks. And then there's a series of recycling and free cycling. This takes time and needs love and effort. It doesn't just happen. We tried to do it on lots of projects. Everybody loses interest. So you have to say up front, if you're going to enter this process, you've actually really got to take it seriously. You need to schedule things, you need to identify what they are, you need to tell the builder to set them aside, and you need the client to put them on free cycle and be ready for collections and all that. It really is an effort and needs to be done. It's very, very rewarding. So we're some windows, some of the building materials, timber, carpets, and kitchen. This is what it looked like when the house was built. So I'm taking you back in time to 1901. When we started this project, I sketched this graph, and I wondered whether through the course of this project we'd actually be able to quantify this properly with real carbon and see if we can really, really try and understand this project in fine-grained detail. So we also wondered about these two scenarios, the higher embodied energy retrofit with a lower operational energy, or perhaps the much lower embodied energy retrofit with a slightly higher operational energy. It turned out quite different to this. So we followed a life cycle analysis approach, working with Jane Anderson. Quite frankly, without her, I would have got lost in this process. It's pretty complicated, pretty detailed. I'm not an expert on it, but I've certainly learnt a lot on this journey. So now, I don't know, put your hand up if you know what an EPD is. Not many of you. Stands for an Environmental Product Declaration, and it's a full life cycle analysis of a project. Looks at the whole life impact, carbon, and all the other aspects of producing that material. There are a lot more EPDs around. There's obviously the ICE, so we're collecting data from many, many different sources and pulling it together. It's still not holistic and consistent, but we've tried our best, and we're sort of getting the best case representation of carbon, embodied carbon that we can. So we measured the brick, all the brick in the house, all the insulation that was going in, all the windows, all the timber, and all the other bits. Had a lot of schedules. It's really detailed. I kind of wished it was done in BIM, but then that maybe doing it this way has given us a slightly closer feel for the data and for the information. So it's been pretty time consuming. So basically you need to measure the volume of everything and know the density and the carbon impact of everything, and then you can work things out. It just takes a while. So in terms of the scope, we did actually get planning permission and building control approval for a loft extension and solar PV, but that's not happening. So the scope of the study is the ground floor and the first floor, and that's going to happen in 2 building phases with a baby in the middle. So there's the proposed ground floor. You'll see that we've got a very small little bump out extension towards the garden. At the top is what we call a standard or a regular extension, and at the bottom is what we call our minimal intervention. So there are a number of options we looked at in our early feasibility study with our client, where we're looking at removing walls and opening up space and making a bigger, wider extension. And so what we thought it would be helpful to look at in the study would say, okay, well, through that schedule of decision making and that, can we make it minimal? Can we look at what the avoided carbon might have been? So what might we have done, or what might another architect do using standard construction materials, and then what did we do using a low carbon approach? So the foundations was completely fascinating, and I think because of time I'm not going to be able to tell the whole story, which is probably a little bit frustrating for you, but what we did is we looked at a concrete raft. So that was the first thing that our engineer came up with. And then we thought, well, hang on a minute. We've still got some concrete of the existing extension. Let's save that, and we'll build off that, and then let's sort of just add a little bit more. So we managed to reduce the size of it. We then thought, well, what about steel helical screw piles? That's quite low intervention. Still quite high embodied carbon. So if you look on the left, you've got impact at construction, module A. the steel piles are surprisingly near the concrete. That was like, whoa, really? Sort of a bit of a surprise. I thought it would be a lot less. And then we thought, well, timber piles. Let's do timber piles. Great, but 4-meter long, 300 mil diameter, get them in the house, buildability, not so easy. Could have put something on the ground, something more horizontal like sleepers, insurance issues, general sort of insecurity around that. So we then sort of just went back to very small, cement-free, chem-free is a product that's out at the moment. People are talking about it. I'm not sure whether we ended up getting an EPD on it, but we did get information that Jane has managed to use and felt was valid enough for the time being. And we ended up getting our engineer to design the tiniest little pads with reused bricks on top of them and doing a little suspended timber floor over the top. And that turned out to be, in the overall impact, module A plus C, higher than timber piles, but still lower than the other two. So it was sort of entering into this process and analysing that we managed to get a lower carbon solution. So on the left is the client's combi boiler, and on the right is a radiant panel, electric radiant panel. And you'll probably all be familiar, well, I'm actually, are you familiar? But, do you understand what decarbonisation of the grid means? If you don't understand, put your hand up. Okay, just a few of you, so I won't go into that, sorry, but it basically, the carbon content of electricity has massively decreased, and so producing heat through electricity, which was, 5-10 years ago was, no, you wouldn't do that. Now suddenly it's become a much more viable option. And so we've been looking at radiant panels. I suggested it to our client and said, why don't you look at this? And they said, and I said, Sarah was a little bit skeptical, a little bit dubious, and I said, why don't you get one and try it out? So they bought one, a reconditioned one, and just tried it out for a few months and actually quite liked it. So they are now going to have radiant panels. And we looked at an air source heat pump. So this looks at life cycle assessment, comparing an open coal fire to a combi boiler to radiant panels and an air source heat pump. We didn't go for the air source heat pump because of the issue of where to put it at the back of the house and acoustic issues. So we've also looked at insulation materials in very, very fine detail, and that was really a rather fascinating journey. We've got some very, very interesting, helpful data now on a whole range of materials, and it's pretty obvious that if you use cork or wood fibre and you take account of sequestration, that you are locking in very, very large amounts of carbon into your project. It has to be detailed well. It's critical that it's detailed well, but you are locking very high amounts in. And probably it's worth saying that a lot of insulation products are actually bonded to walls. So there's a plaster, and then it's bonded to a wall. On this project, what we've done is there are some systems that you can screw straight to brickwork. I like to plaster the brickwork to get the air tightness right and to deal with any potential water ingress through the wall that might then affect insulation. So I think that lime plastering a brick wall and getting it really, really plumb, and then fixing direct insulation, wood fibre insulation to the wall, getting a really tight, nice, snug fit, but not actually bonding it to the wall, at least gives you the opportunity of taking that insulation away and reusing it potentially in the future, rather than it having to be broken off the wall, which is what happens when it's bonded to the wall. So we also wanted to compare a standard steel lintel to a timber lintel. We just wanted to see, well, what is the difference? It's pretty huge. It's at least 4 times more carbon in a steel lintel than a timber lintel. So back to this graph. I just got really fascinated in this history of a building, that it goes through coal, timber, coke, open fires. It goes into a period of poorly performing gas boilers, slightly better gas boilers, condensing gas boilers, and then suddenly now we're at this stage where a whole range of new technologies are opening up. And the big question was, we're going to do a retrofit now. There's a climate emergency. we are looking at a very, very bleak future. Should we be releasing carbon into the atmosphere now? We've got to sort this mess out as soon as possible. So what kind of intervention are we going to make? So in order to quantify this drawing, I produced this schedule of building elements and then trying to look at the frequency of repair and frequency of intervention on each one. And then Jane has added carbon impact to those numbers. So that's helped us actually quantify it. And funnily enough, the graph doesn't look that different to what I drew initially. So this is a properly quantified version of it. And so on the left, you can see the emissions on construction. So that's tons of carbon. And you can see a whole series of interventions through its project life. Obviously, this is speculative. We know some of it, but not all of it. And then you've got 2020, this moment now where we're going to be retrofitting. So overlaying that is just a look at the carbon content of the operational energy. So this is, very. I mean, if you look at the carbon emissions of the coal burning, back in the day, and then of course now we're looking at rapid decarbonisation of the grid. We're looking at producing all our heat from radiant panels and our hot water. We're going to be using something called a sun amp, which is a heat battery. So it's a very small device, looks very, very promising. And then our client isn't currently installing PV, but that may come in the future. And I have to say that I'm a little bit skeptical about the carbon emissions of PV. A lot of stories have changed over time, over the years. And Jane, when she looked at the carbon content of PV, I haven't put this on the slides because I don't know about this yet. You go to any PV supplier and they say you save carbon immediately, but you don't. There's a pretty large carbon burp at the start of producing those panels. And I'm not sure how much. It very, very, very much depends on where it comes from, who makes it, and how they make it. So all I urge you to take from this comment, is that where something comes from and how it gets to you and how it's made is critical. So, for example, some Norwegian panels were significantly lower carbon. There's something called a solar scorecard that is a very useful measure of the impact of solar panels, and I think that's really worth looking at. So you remember this graph. So we've looked at what was the original construction. So this is just module A, so basically the carbon emissions of producing the building, the stuff. And basically you'll see that our retrofit is carbon negative. It's because we got so much wood and wood fibre. I was really surprised. I just didn't think it would be like this. I really thought we must be 2 or 3 tons. But when you look at sequestration, it's actually carbon negative. The standard retrofit was about 12 tons. So there's really, the take home from this is that there's significant reductions of carbon can be made through initial layout decision making, through very careful specification, and through a kind of really strong desire to find good homes and keep these materials circular, keep them flowing. So back to the graph that I speculated on. So there's our current operational energy. So this is actually operational carbon. So this is if we just left the building as it was. That's what's going to happen. If we did a standard retrofit, that would be our carbon burps. That's 3 months worth of construction, about a 12-month burp. Then we would have had that kind of operational energy. In fact, we've done that, and we're going to have that. So we've got a pretty massive avoided carbon impact. Okay, so that's the end of the case study. Any questions on it, feel free to ask me afterwards. We might have some questions now. I've got a very quick thing, which is, I just want to tell you about Raft, which is Retrofit Action for Tomorrow. It's a not-for-profit, and I'm working with schools with a program where I engage the children and the teachers and the entire school community, teaching them about building performance, about the climate emergency, about the circular economy. We've been making models, so we've got something called the Baked Potato Challenge, where I get them to insulate a baked potato with natural insulation materials, and then they learn about thermal continuity and building performance. We then use a thermographic camera and analyze them and see which one kept the heat for as long as possible. And I'm in the process of producing a zero carbon retrofit plan for this school. And then my last point is that this was a petition that I started before there was a general election. It's since been shelved because that's what happens to petitions. It only got to about 4,000 names despite telling everybody in the world about it. I just have to say that I think that one of the most significant impacts we can make on stimulating a low-carbon, deep retrofit market is to try and get a 0% rate on retrofit works. And I think it's really, really important, and I'd be very grateful if you could share that message to people. Government are always saying, how can we reduce the cost of retrofit? Well, this is the answer. This is 20%. This is the difference between a deep retrofit and just an extension. You know, it really is a very big opportunity. Okay, thank you very much.
Thank you, Harry. That last point about VAT is a huge one, and I'm glad to say that I did sign your petition. I was surprised that more people didn't, because it's obvious. The Green Party had it as part of their manifesto to do something about the VAT on retrofit, because obviously the point is, if you're doing new build, it's zero rated, and so we're actively encouraged to demolish at the moment. Harry, that was an amazing presentation.
Thank you.
When are you writing your book? Seriously. I mean, it's a lot of data there.
Yes.
Are you doing this? Is this ongoing research you're doing, and whatever clients that you're working with can dip into it? I mean, it's quite a lot of people working on quite small projects. How do you make that work?
I was up late last night.
What about the other consultants you're working with?
Jane's doing a PhD, and she's very happy to have that part of her project. I think, I do call in favours. So we're just giving it love. We don't have special funding. It's challenging. It's not easy.
But you're doing retrofit properly, in my case. That's what I wanted you to hear. Show everybody how it's done. So you can learn from the amount of time that you put into a project. I mean, are you beginning to think about moving forward to sort of being able to wheel it out, roll it out, so it's commercially viable in terms of clients being able to afford the consultants to do the job?
Yeah, it's a really good point. I mean, I think the fees associated with a really great deep retrofit are difficult. You can see that even on my own house, I was doing my own drawings. I would have loved to have got somebody in the office to do them, but I couldn't afford to pay them. So it's an ironic situation. So that's why I did watercolors and produced them myself. Since January, so since the new year, our office has had a massive number of new inquiries. They're all projects that are, I don't know, about 50,000 to 100,000, may or may not involve extensions. This is the market for retrofit, for deep retrofit in the country, and we are working on a way of delivering a lower cost, still very robust service to try and service this. I think it has to involve people that are going to carry the work out. Always thinking about setting up a construction company in parallel with the business so that I can offer a kind of one-stop service. That's another whole story. You can see we're busy trying to do the research. But I'll offer one idea. But it's just a recent idea I've had. It's just that there are a lot of people with money out there, and people do want to do good. And I think that a really amazing initiative would be to think about setting up fantastic case study projects on quite a fine grid across the whole country, so one per 1,000 houses that are representative of the houses in those areas. Retrofits carried out for free, and the people that get it, they're obliged to open up their house and to share that learning. So there'll be a local architect who's experienced in carrying out this kind of work, who can show people round and can educate, and people can come round and see the project. And then there might be some kind of pattern book. So you could say, these are the 3 different insulation materials you could use on your front wall or your bay window. And I think having something local, referable, could be a very powerful way forward. But
Right, I'm going to let other people ask questions. So Nick's already put up his hand. Are there any other people that want to ask questions? Put up your hands there. So there's 2 here. Anybody else? One more. Okay, I'll ask Nick.
Thank you. You kind of slightly answered the question in a way that presumably most of those pictures would be representative of types, yeah? So in a way your pattern book is probably realistic to some degree in a lot of places, isn't it?
Yes, it's getting
the lion's share of estates are one type of house and even one type of shape. And just as a reference, we did a project on retrofitting in terms of just insulation for the Green Deal and so on. And part of the penetration and success we got, which was 80% of houses in one village, was on that basis of just picking 4 or 5 houses that were the same, saving lots of money by almost rolling out the repeats of that, and then also building up, like you say, that the kind of trust around that, which I think your idea is a really good one for building trust.
Yeah.
So people can go and see something and entrust in the fact that their money is going to be well invested, which people are really very skeptical about the complexity of this because they just don't understand it. But
I don't know if any of you are architects or work in the building trade, but there used to be these things called local district surveyors who worked in building control. Now we have approved inspectors, and it's sort of paper pushing really. But there used to be people that knew their area. They knew the types of houses, and you could actually, they would say, oh yeah, on those houses the joists go this way, and and I think having that kind of local knowledge is it builds trust, because people know the idiosyncrasies, and there's a real dilemma here that we want to mass roll out retrofit, but all buildings are different. Even buildings on the same street might have been built slightly differently. Some might have stud walls with brick infill on edge, and others might have lath and plaster, and there's so many little differences that buildings have. So there's a fine balance between getting a pattern book and pushing it out, and then having sort of that local knowledge.
Who else?
Thank you so much for your presentation. I wanted to know what the difference would be if you actually incorporated BIM in your calculations and the design, rather than the way you did it now, which was obviously very energy intensive on your part and your consultant's part.
Yeah, I think it would be quicker, smoother. It would give us quicker answers. It would. I mean, we didn't really charge fees for this, so this is for love. But let's say we were charging a fee, it would be a lower fee. So I think it would be a lot more efficient. We're a small practice. We don't have big resources. I wish I could just train everybody up on BIM. But like I said, I think we learnt a lot by doing it by hand. It's a bit like me doing my DIY by hand. When you're very close to the data, you feel it and you understand it better. With BIM, perhaps that sort of automation of spreadsheets being produced from volumes, it happens in the background, and you don't get that feel, and that feel is really important, I think.
Thank you.
Any other questions? Yes.
Thank you for the inspiring presentation. One question which I don't quite understand: how can you be carbon negative in your building work?
Yeah, so wood. So when a tree, this is one of my bugbears, is that sometimes people talk about cutting a tree down and replacing it with another tree, as if an old 100-year-old tree is the same as a tiny sapling. Every year that a tree grows, let's say a mature tree that it might be 100 years old, it puts on, let's say, 1 or 2 millimeters of wood on its whole surface area. So you think a really large tree, that's actually a really, really large volume of wood, and that wood is carbon. Yeah? So compare that to a small sapling, it's nothing. Yeah, it's a tiny amount. So wood is timber, trees as they grow, they sequester carbon. Yeah, they lock it into their trunks and branches. And so when we cut them down, we are effectively holding that carbon. So if you then build with that and you build responsibly, you can lock the carbon into the building. So that then becomes sequestered carbon. Yeah, and I was shocked with those numbers. I double-checked, rechecked all the volumes and the weights and everything. So really, is it really? Yeah. So, that's how it is. And we've got a lot of wood fibre in the building. When you put, if anybody's done a project that involves delivering insulation to site, you'd be really surprised at the sheer volume of the material. So you cover the surface area of a building with insulation. It's actually very large volumes.
Any more questions for Harry? Yeah, one more here.
So following on from what you just said, you've cut down a big tree and sequestered it, but what about the little sapling? Did you take into account the fact that that tree is now not taking any more CO2 down?
I didn't completely hear. There's a lot of noise from over there, and I think the speakers are going that way. Can you just say that again?
Yeah, following on from what you just said,
Yeah.
You've cut down a big tree and you've planted a little sapling. Did you take that into account? You've sequestered the carbon, but it's no longer being drawn down into the tree.
Yeah, sustainable management of forest is obviously critical. So any timber, So generally we like to procure timber locally as far as possible, and then to make sure that there's a full chain of custody all the way through to make sure that the timber is replaced, that the place where it came from is sustainably managed, and that the timber is being replaced, for future life. So I think the answer is that yes, you have to manage forests sustainably, and that tree will grow, but you need to plant many more trees, saplings, to get anywhere near the carbon of big trees. So I'm just very skeptical about carbon offsetting and just, it's still a good thing. It's still a good thing to grow trees. But you also have to think about biodiversity. But I'm talking about sustainably managed local forests where you might be thinning, you might be taking timber from pollarding, so the tree is still growing. Pollarding is where you cut a tree at about 2 meters high, for example, and you use 15-year growth, but the tree still keeps growing and then it grows again. So there's a lot of different ways of harvesting timber, and chestnut pollarding and coppicing is something that's been done for generations in the UK.
Yeah. Hello there, Charlie Law. Hope you can hear me there. Just following on from that on the tree side of things, older trees actually tail off the amount of carbon they take in. So actually it's better to actually harvest a tree in a lot of cases and plant new ones because they then take the carbon on a lot quicker. So that's another reason for harvesting trees. And the sort of timber Harry's probably talking about, probably a softwood timber that you used in the main. Is it softwood timbers that you've used in the main?
And some hardwoods like chestnut or...
Yeah, well, chestnut is
ash.
hardwoods, but they're generally fast-growing species anyway.
Yes,
So an ash is like something 60, 70 years. Softwood's generally 50, 60, depending where you get it from. So the timber side is great, and the numbers are real. There's a lot of work going on in that, and it's great to see you using a lot more timber. I've got a question as well, if that's all right, quickly. Just on the insulation side, you say you use a lot of wood fibre insulation on that.
Yeah.
Don't you find that you lose a lot of space internally with that? And have you got clients
it's
an issue with that?
The specification of the thickness of the internal wood fibre is quite carefully designed. So you've got to look at both the moisture loading on the wall. So a brick wall gets rained on, it absorbs moisture. That moisture then moves through the wall. You have to be very careful if you add too much insulation. You're not getting much drying action, so you're also starting to get the risk of a raised moisture profile where that insulation meets the wall at the cold spot. So generally try and avoid putting too much on. It's on a room-by-room basis. To keep things simple on this particular project, on the second case study, we've got either 40 mil or 80 mil of wood fibre. So where space is a bit more of an issue, we've gone for 40 mil, and where it's not, it's 80 mil. I think 80 mil loss of space is a small price to pay. Yeah.
Okay, we could have one more question if there's one on the floor. One at the front here.
Hi, I'm interested in the cost to the client of what you're doing. What you're able to achieve on the type of budgets you're talking about is incredibly impressive. Do you feel, compared to a standard architectural approach, that you're absorbing the sort of conscious changes you're making in terms of reuse and making decisions about whether or not to demolish parts of the building? Is that are you then able to absorb these additional measures you're doing within the client's budget, or do you think it adds a percentage cost onto the overall bill?
Yeah, quite a big aspect to this is client time. It's actually quite challenging being a client. It's hard work, as most people would know, and then doing it this way is a bit more challenging. But I think a lot of us are moving towards an existence of being more responsible throughout all the things we do, and it might be how do you procure your clothes and what how do you procure your food and your food waste and all these processes. And I think this is about lifestyle, and it's about actually incorporating it into your lifestyle. So this particular client have done that, so they're using their time and their love to sort of deliver some of these aspects of the project. But just maybe it's helpful if I talk a little bit about costs of projects. So we've looked at, myself and a colleague who runs another practice, Pruitt Bisley, Bob Pruitt. We've looked at, I think, about 8 of our projects and 8 of their projects, and we looked at the pounds per square metre for each project in terms of the retrofit measures. And we found it to be at around £500 for a really robust deep retrofit project, and that seems to be the sort of the rough building cost for the projects.
Harry, could we make that £600 a square metre so you get paid properly in terms of your time? I mean, that's sort of a flippant comment, but not really, because we need to spend money in a slightly different way to solve the new problems that we've got, or the old problems that we're now waking up to. I've got to wind you up there. Thank you very much. Can we have a round of applause for Harry?
Thank you. Can I add, do you mind if I just add one more thing? Because your brain is working. I just wanted to answer your question a little bit better. A number of the decisions we've made was a bit more design time, but saved the client a lot of money.
Yeah, that's why you need.
It's really hard
your
to.
Fees worth
you
it.
can't. We saved them so much money by saying no, don't remove that wall, and if you remove that wall, you start getting involved with fire issues and fire shutters, and just don't do that, and do it like this, and then you save £15,000 with one decision. So there are a number, by keeping it simple and low carbon, you actually save a lot of money on the project budget. Yeah.
Thank you very much. No, it's all right. I've got to go somewhere else very quickly. Thank you for being here now and seeing Harry. It is a glimpse at a very near future, as far as I'm concerned. This is a sort of attention to detail that clients and designers need to put in place to solve some of the big problems. We've got the big innovation pitch here at 2:15, so come along for that if you want. Thank you very much, Harry, and
thank you.
Thank you.